Good morning, good afternoon, good evening, wherever you are. It's brunch somewhere, and welcome to Future Brunch. We are stoked. We've got such a great conversation lined up for you today because we are joined by Kirsten Banks, who is an awesome young astrophysicist, and we are going to be talking about all things space today. So Kirsten, welcome. Thank you very much for joining us.
Thanks for having me. I'm so excited to talk about space for a full hour. It's going to be awesome.
We're pretty excited too. My name is Gus Harvey. I'm one of the co-founders of Future Crunch. I'm a political economist and a long-suffering space nerd. I want to acknowledge, before we go any further, that all three of us are broadcasting on the traditional lands of the First Nations people of. This is stolen land. Where I am, in Melbourne, these include the lands of the Bunurong, Bunwarang, and the Wiradjuri Woiwurrung peoples of the Eastern Kulin Nation, and their name for the place that I'm broadcasting in specifically, Fitzroy, was in Ngarigo. Tane, where are you broadcasting from?
I'm from Maribyrnong, which belongs to the same people, and Maribyrnong means I can hear ringtail possum. So I don't hear them this morning, but occasionally you can.
Yeah, great. And Kirsten, what about you?
I'm sitting on the bundling people. Sorry, I've just lost everything that I was going to say today. The Bedigal people of the Eora Nation, and I'm very privileged to be sitting on their land today and acknowledge the elders past and present of this land.
Wonderful, thank you. All right, let's get into it. I'm sorry, by the way, before we get into it, let's not get into it yet. We would love it if everyone who's tuning in and who's live right now could just tell us where they're from. You can put it in the chat box, which is over there. I don't know which way. Would love to hear where you're from and where you're tuning in from today. Please use the chat box throughout the conversation. If you have any questions for Kirsten at any point, put them in the chat box or put them in the question box down here, and we'll ask those questions to Kirsten during the course of our conversation. All right, Tane, over to you.
All right, well, I just want to second that. We are part of this land. The land is part of us, and we invite you to join about learning about the universe, the place in the cosmos that we find us, and also, you know, the land alongside the indigenous communities here in Australia and across the planet and throughout the universe. So let's get started. The main thing I'm excited to ask you about, Kirsten, is when did you first discover the passion and the love of looking up at the sky and thinking about the stars?
Oh, I love thinking back to this moment because it was such a pinnacle moment in my life that really just springboarded me to where I am today. So I was in about year 9 or year 10, and my science teachers took my entire year group out on an excursion to go see the Hubble documentary on a massive movie screen, like the IMAX version. Yeah, right? Like it was so cool. So I remember sitting there as a 14, 15-year-old girl with the one-size-fits-none 3D glasses slipping off my face, but just looking up in awe of these fantastic photos taken by this phenomenal telescope. I saw these, thought they were just absolutely beautiful, and realized that's what I want to do. That's what I want to study. I want to find out more about our mysterious and beautiful universe.
Great. So you've been at it ever since, really.
Pretty much.
And you know, it's obviously been a huge passion, and you've been very successful in sharing that passion with a lot of other people. If you kind of bring it into the current era, this year, what has surprised you the most in 2020? What's been the biggest surprise or the most exciting piece of news that you've heard space-wise in 2020?
Oh, there's been so many in 2020. Like 2020 has just been delivering for science research and science discoveries. I think the biggest thing of 2020 overall would have to be, and probably a little bit contentious as well, just to see where it goes, is the phosphine being discovered in the upper cloud decks of Venus. Like that was a big discovery.
Okay, can you tell us a bit more about that? Can you explain what they've discovered and what it means?
Sure. So astronomers have been looking at Venus and observing Venus for a very, very long time. Although despite the fact that Mars has always been a bit more of a bigger subject when we talk about potential life, because Venus, it maybe used to be like the Earth. It's very, very similar to the Earth in the fact that it's the same size and about the same gravity as well if we were to stand on Venus. However, if you were to stand on Venus, you would probably melt because of the very, very thick atmosphere that's made up of mostly carbon dioxide. So it acts as like a very big, thick blanket around the entire planet, superheating the surface up to about 500 degrees Celsius. So doesn't sound very habitable at that point. A bit hot, a bit steamy, but astronomers have found traces of phosphine, which is an organic chemical, at least as far as I'm aware. I'm not a chemist, so for the chemists out there, I'm sorry if that's wrong, but it is a compound that is only produced on the Earth through biological activity. So it's very exciting to see that in the upper cloud decks of Venus, because maybe it might lead to life. But there was a huge breakout of this information. It was leaked a little bit the day before the embargo was lifted. So it was bit of an issue there. And as the media goes, it's very funny. I love the media because I'm in the media a lot, and I do love to share my passion for astronomy throughout the media and social media as well. But with this leak, and even with that leak as well, after just the main result was presented, almost every single news platform said, "There's life on Venus. We found life on Venus." It's like, no. We didn't. We just maybe possibly found a biosignature. And even then, the researchers, when they actually presented their material after the embargo was released, they said very specifically on a slide in their presentation, "We do not claim this to be aliens, or we do not claim this to actually be a confirmation of life on Venus." So I think that was definitely the biggest and caused the biggest uproar of excitement. But it had a bit of a catch-22 with it too.
Yeah, absolutely. The media always does a great job talking about science. They're so factual, they keep all the facts golden plated. Speaking of planets and also exoplanets, like Deborah Fisher was one of my favorite astrophysicists because she was an explorer of new worlds, right? She was like a Cook, a Columbus, a Magellan. And they look at hundreds of planets outside the solar system, around other suns and stars. And you love the formation of stars, and it's crucial to why we're here and all of the billions of galaxies within the visible universe. So tell us what got you hooked and how you look at these stars from across incredible distances.
Well, if I'm honest, so my research career, last year that kind of started with my honors program, which is kind of like a mini thesis, the 1-year thesis program at the end of an undergraduate degree. In that project, I actually worked on distant galaxies. So galaxies that I like to call it a tale of galactic cannibalism. So you have these really massive galaxies at the center of galaxy clusters that attract their neighbors and merge with their neighbors. And so they eat their neighbors. Galactic cannibalism. But the reason why I moved on to stellar astrophysics this year, starting my PhD, honestly, for 2 reasons. Number one, my supervisor. So both my supervisors from honors and now in my PhD are absolutely wonderful people. Funnily enough, they're both named Sarah, so I didn't have any problems remembering any names, which is great. But number 2 is the scholarship in the program that I am working on. So with a PhD, usually what you do when you apply for a PhD is you choose a project yourself. Like you come up with something yourself, come up with a question to answer, and you apply, and they say, "Yep, that sounds good," or "Nah, we don't think you're good enough," which hopefully is not that one. But in this particular program, the project was already chosen. So already chosen by the university. So I applied for that particular project. My supervisor now, back then, said, "Yep, like Kirsten to be my little PhD student." And then the university say, "Okay, you seem good to do this, have some money, and do this research for 4 years."
Okay, and what is the research going to be? I mean, what do we not know? Don't we know lots about star formation? Haven't we kind of got it all figured out? Or what do we, let me rephrase that question. What do we know and what do we still not know about how stars are formed?
Okay, so we do understand a lot about the formation of stars. You have these large, giant molecular clouds. This is a fancy word for nebula in space. So lots and lots of cloud and dust and gas in space, that within these molecular clouds, they're not quite uniform in density. So there are some clumps here and there that have more stuff, they're denser. And those denser regions attract and accrete material from less denser regions around them in space. And eventually all of that comes together to form stars over millions of years. It doesn't quite happen just like that, although I wish it would, so then we could see it more often. But we do know a lot about how stars form, but through that, we still don't know a lot of things about the history and formation of our own galaxy and galaxy formation. So what I'm doing is I'm studying the stars in our Milky Way Galaxy to try and understand more about the history and formation of our own island universe, to then extend that to other galaxies. How do galaxies form as a whole? How do they evolve as a whole through where chemicals tend to be found? So is there more nitrogen over this part of the galaxy, more carbon over there? What's going on? How can we figure this out?
Yeah, that's an easy question to answer, I'm sure. So, I mean, like, what I love is when we look out to the furthest reaches of our universe, you know, a journey through space, but also through time, which always blows my mind, is that we know that all the atoms and the molecules, you know, in the cosmos that construct us, our brains, our technology, you know, they're traceable to the crucibles that were once the centers of like high mass stars that collided and like exploded and seeded the vast clouds that you talk about with the seeds of life. So as we gain this incredible knowledge, I feel like it gives us empathy to not only each other, but to all life and looking outward towards the stars. Having said that, do you see differences in these chemicals that were fused in the cores of stars? This star dust, is it different in different galaxies or across the Milky Way?
So I haven't quite gotten that far into my project just yet. So maybe come back in a year or two and we might be able to have more of a conversation about that.
All right, we'll put a pin in it.
We'll put a pin in it for now. But that's one of the main goals of my project, is to produce a detailed 3D map of our Milky Way Galaxy and see where those abundances are throughout the galaxy.
Great. So now, with regard to that, we heard recently that you got yourself a really awesome early Christmas present.
I did? Oh, I did. Yes, I did. So during the project, we would like to observe some stars in the Milky Way Galaxy. And so earlier this year, around March, April, when I first started my PhD, myself and the team we applied for telescope time with a proposal. And we asked for 15 nights and we got 15 nights. So I'm actually going to be starting observing next week. It's going to be exciting. I'm going to get some targets, get some data and try and work on things. But the other half of my time is right over Christmas. So I'll be observing from the remote observing room at my university, dialing into the largest optical telescope in Australia at Coonabarabran from the 22nd of December all the way to the 27th of December. So for all those kids out there, I'll be looking out for Santa.
That's great. What I really love about the story is you told us a little bit about how, and this I think speaks to science more generally, or certainly science as we would like it to be practiced. You said that when people apply to use the observatory for observing, it's a total meritocracy. So all the applications are done and they're anonymous. So the applications are chosen purely based on whether the people who run the observatory think they're a good idea or not. They're not linked to names, they're not linked to identities. That to me actually feels like quite an extraordinary practice in a world where there seem to be so many divides, especially around identity. Can you speak a little bit more to that, around kind of the meritocracy, whether either the evidence of meritocracy or the sort of the lack of evidence of meritocracy in your field?
Well, it's actually helped a lot in my field. So astrophysics is very much a male-dominated field, as many other streams of physics are. And without this, anonymous merit-based system, more often than not, men would get more of these proposals accepted than women would. Then again, there are more men still applying for these too, so there's a little bit of bias there just based on the sample size. However, with getting rid of all of that, making it all anonymous, making it all based on the merit of the actual science that you're presenting, even with the proposals itself, you're not allowed to refer to your own work. Well, you can refer to your own work, but you refer to it anonymously still. All of the citations are just numbers. They're referenced at the bottom of the proposal, but within the actual text itself, it's just numbers. So source 345 did this. We like to expand on this, so on and so forth. So it's really, really great that way. Because if you think about it, let's say, I was the principal investigator for this particular project. I just started my PhD. This is the first proposal I've ever put in. Realistically, would you choose me? Probably not, right? Because there's people who have been observing for years, sometimes even decades, that will probably be more, trusted with the telescope and that sort of stuff. But with it's just based on scientific merit of the project itself, it's improved those statistics so much.
And sorry, last very quick question. How long has that process been in place?
At least a few years. I don't know exactly how long it's been in place for this particular organization, but it has been in place for a while.
Okay, so it's relatively recent.
Yeah.
Right.
Well, it's always good to interject, and inject new ideas into old ways of thinking. But the old ways of thinking are incredibly powerful. Like, I'm a sailing nerd, right? I love sailing. But people who used to sail around the globe used to navigate by the stars. And there's huge knowledge, from our past about how the solar system moves and how the night sky changes through the seasons. And so while that's incredibly powerful for sailing, it's also incredibly powerful for land dwellers. So what I loved about reading some of your stuff, which is pretty cool, is the Celestial Emu and how it gave us a view onto the life cycle of one of the most iconic Australian birds through the Indigenous lens. Can you tell us about the Celestial Emu?
I sure can. And I'll tell you it from my Wiradjuri perspective, because the perspectives do change from different countries that do observe the emu in the sky, this dark constellation. So I'll start with actually explaining what it is. I know there are a couple of people who are watching today who would know what it is already, because they do listen to what I have to say online and all that jazz. But for those who aren't aware of this, it's a fantastic constellation. It's my favorite constellation of all the different star laws, both Western, Wiradjuri, Aboriginal constellations in general as well. It's great because it really changes your perspective of the night sky. When we look up at the night sky, usually from a Western lens and a Western perspective, we look for the stars and we connect the dots. We connect the stars together to create these asterisms, which we then call constellations. And some of them make sense. Some of them take a bit of imagination to figure out what they're supposed to be, but they're all generally dots and stars connected together to create these and manifest these images. But with the emu, we completely ignore the stars. We're actually looking within the Milky Way Galaxy. So if you're in a really dark place with very little light pollution, you'll see the Milky Way Galaxy stretching right across the entire night sky at certain times of the year. It's huge, it's massive. But then what we're looking for is we're looking in the dark spaces of the Milky Way Galaxy. So when we do look at the Milky Way Galaxy, it's not just a complete carpet of stars or a complete carpet of just brightness. There are darkness and negative spaces within this Milky Way Galaxy, and that's formed from the dust and gas that exists within the spiral arms of our Milky Way, within our island universe. And it's not that there's a lack of stars there. There's still an abundance of stars, but there's abundance of gas that blocks the light naturally from these distant stars. And it's within those dark patches that we see and observe an emu. And if you like, I can share my screen and I can show you a virtual version of that. Let's see, I'll make sure that I have everything all sorted. Yep, all right. Let's see. Okay, share screen. Technology.
Technology.
Okay, can you guys see a nice sunset?
Yes.
Excellent. So I've currently set it to my location in Sydney, and around the end of May, so this is the best time to see the emu rising in the sky after the sun has set. So we are looking towards the west, kind of in a sort of outback sort of scene. We're not going to have the light pollution of Sydney, because as a Sydney person who's lived here all my life, light pollution here sucks. So we're going to turn off the light pollution once the sun goes down. But I don't want to look. We'll have a quick look at the sun going down, because it's kind of pretty. Okay, down we go. But as soon as some of the stars start to come out, I'm going to rotate around. I'm going to look towards the east and see the emu rising. Let's see, that should do. Eventually, it'll start to get darker and darker. Some stars will start to come out. This little thing over here is just a meteor shower. I'm going to turn that off for now because we don't need meteor showers. Okay, we can see some stars coming out. We'll look this way a little bit further towards the southeast. And eventually, the Milky Way Galaxy will start to appear. Can you kind of see it there?
Yeah, there it is.
There it is.
Right.
So I've got this on our sort of perspective that we would see. So it is going to look very big. We'll have to look around with the screen. But let's fast forward a little bit further. So after the sun has gone down in this sort of mid-May sort of area, early June, this is when we see the emu on the horizon after the sun has set. And it's when it's on the horizon, it looks like it's running along the horizon. So let's zoom out a bit so we can get a bit of a better look. Okay, so you might better see it here. So if you look very closely, you can got the Southern Cross up here.
Yeah,
this
totally.
dark patch, I might go a little bit closer. There we go. This dark patch here in Western astronomy is known as the Colsack. It's a dark nebula. And so that makes up the head. It's kind of a beaky sort of thing here and a head up there. And this long column of dark dust here is the neck. And then the bulge of the Milky Way Galaxy, which is the central bulge of the Milky Way. That's the center of the Milky Way Galaxy right there. That's the body of the emu.
That's amazing. So what does it mean? I mean, what can we, it's not just a pretty picture in the sky. It was actually useful to our ancestors, wasn't it?
That's right, yes. So when the emu is in this position on the eastern horizon, it looks like it's running along the horizon. So that matches and mirrors back down on the Earth, saying that the emu are now running around on the ground looking for a mate.
That gives you time of season. It tells you which foods are available, which ones aren't.
That's right. So right now that tells you that the emu eggs are not available just yet. Okay. But later in the year, we're going to fast forward by a week. Okay, you can see as we're going ahead, each step is a week gone by. So we're now in late June. But later and later and later, you can see that body of the emu is going right above us. And eventually, when it is directly above us, directly overhead, this is usually in the darkest part of the year, or the coldest part of the year, rather. At this point, from my Wiradjuri perspective, we now see the body of the emu not as a body anymore, but instead as an emu egg in a nest.
Wow.
That's awesome.
Right? And that tells us that now is the right time to go looking for emu eggs.
Yeah, wonderful. That was very cool. Thank you, Kirsten.
My pleasure. I'll see if I can stop sharing quickly so I don't get the time warp.
It's so cool how, look, put it this way, I grew up in the northern hemisphere, and learned all the constellations. When I fell in love with looking at the sky was when my dad took me out and we used to lay on a lawn chair, and there was low light pollution because I lived in rural New Mexico, and he'd point out all the constellations, and I learned them all, and I was like so excited. Orion's Belt, Big Dipper, much more boring than emus. But I remember just noticing how they changed throughout the year. And it really didn't come into full perspective until I sailed across the equator. And then everything got flipped, and then new constellations were coming out. I mean, the Southern Cross, I'd never seen that before. And that's really cool. But I think the most incredible part is attaching a story or something that is, an icon, like a constellation. And that helps cultures and people like define themselves by the stars. And storytelling is so important, you know, even in science and astronomy, and it makes a huge effect. So what stories do you like to tell that really get people on board, you know, through the lens of the stars?
One of my favorite stories to share is the story of how the moon was created in Wiradjuri Dreamtime. So back in the age of the Dreamtime, you had Bayami, who is the almighty creator spirit, and Bayami has the company of 4 animals. You've got the kangaroo, emu again as well, eagle, and koala, and they're all living on the earth, very happy, in sync, all that jazz. But eventually they start bickering and fighting because they're all fighting that I'm the best. No, I'm the best. No, I'm the best. And so Bayami sees this quarrel happening down on the earth and comes down from his home in the sky with a solution. And he says to all the animals, okay, if you want to prove that you're the best, show us all your greatest thing that you can do, and we'll choose who's the best at the end. And so one by one, all of the animals, they come along and they do their greatest thing. So the kangaroo, what do you think the kangaroo did? Yep, it bounced, it jumped, and it jumped so high, it jumped over tall trees and was very majestic and all that. So the kangaroo jumped, the emu ran, and with the blow of his feet, he beat everyone in a running race. The eagle flew so high up in the sky that you couldn't even see him anymore, but then effortlessly glided back down. That was his greatest feat. What do you think the koala did?
made a horrifying noise.
Yeah, while mating.
Whenever I tell this story to young children, they always say that the koala sleeps, and I'm like, I wish I was a koala. But no, the koala, he climbed to the tip top of the tallest tree, and even with the wind swaying him around, he was not fazed. So they all showed their greatest thing that they can do. Now, before I tell you what Bayami did, do you think any one of those animals is particularly better than the other?
Yeah, I see what you're saying.
Right? Yeah.
Obviously not.
Obviously not. They're all great in their own way, and they should respect each other for that. But then Bayami comes along, the elder, the person who created them, the person who they should respect, comes along with his boomerang, which we call bargan in Wiradjuri. And he throws his bargan so hard that it flies through the sky, it changes shape, it has a life of its own, getting bigger, getting smaller. You might be seeing where this is going to here. And he comes back down and he catches it, and all of the animals are very impressed. But just to prove his point, Bayami throws his bargan again, and he throws it so hard this time that it follows the sun in the sky. And then the next day, after the sun has set, a small crescent moon, bargan, appears in the night sky.
I love it. So
isn't it beautiful?
That's so cool.
Right? It's so cool. And it's I love that story because it represents more about what our culture is about. It's not just stories. It's definitely not astrology. It's science, it's astronomy. But within these stories, there are lessons and lots of lessons to learn within these stories, both of how we should conduct ourselves in day-to-day lives when interacting with the land, interacting with the people, and interacting with the skies. It's all interconnected.
I think it's making me think just about kind of the responsibility, perhaps that people who are regarded as storytellers have in wider culture. There was a question from one of our users, someone called Michael Redshirt, Semperton, who said that he considers himself to be a storyteller for his culture. And I guess that in some senses is true for you as well, in that you're a storyteller for science, but you're also a storyteller for your culture. How do you marry those two things? And where are they where do they work well together? And where do you ever find them in tension? Kind of your responsibility as a Wiradjuri woman and your responsibility as an astrophysicist to tell those stories. Where do they work together, and where do you find them in conflict?
It's a great question because it's kind of similar to the question of, let's say you're a scientist and you're very religious as well. It's like, how do you marry those two together? And realistically, when it comes to my astronomy knowledge and my traditional knowledge, is that they go hand in hand quite often. Because, like I said, our indigenous astronomy is science. Like, it is observational astronomy to the T. Like, my ancestors, they observe the stars and see the changing of the stars and relate that to what's happening on the ground. It's a very intimate connection with the stars and even the planets too. We use the planets for navigation, which is awesome. It's very different from what we were talking about, even with sailing, it's using the stars to navigate, but even the planets too at nighttime, and the moon as well. There's so much knowledge there. But I think while it is upsetting that I didn't learn about my culture when I was younger, I didn't really learn a lot in primary school or high school other than just whatever's in the syllabus. But I learned that astronomical knowledge first and studying at university, but also learning about my Wiradjuri heritage throughout my university process, throughout that. It was great because, yes, I could see when I'm hearing these stories, I can think, wait, that relates to this astronomical thing. That relates to this astronomical phenomena. So, for example, there's a great story from both Wiradjuri and Gamilaroi traditions about the first Aboriginal man to die. And a traditional way of burial in many, many Indigenous regions is to put them inside a tree. And the story, I won't go into too much of the details, but this tree is uprooted and pulled up into the sky, and that actually creates the Southern Cross. It's called Yaran, the Southern Cross, the tree. And then within this tree, it's the home of two cockatoos called Mare Mare. And as the tree is being lifted up into the sky, Mare Mare, the two cockatoos are following their home up in the sky. So if you think about the Southern Cross, what two stars do you often see next to the Southern Cross?
The pointer stars?
The pointer stars. That's exactly right. And with the story, they're constantly following their home in the sky. And if you look very carefully at how the sky rotates and how the sky moves due to the rotation of the Earth, those two stars constantly follow the Southern Cross in the night sky. And so there is that actual astronomical knowledge within that just goes hand in hand almost every single time.
Oh, awesome.
Yeah, and it's across cultures and religions as well. North Star up north. I think quite a large religious body sort of centers around that one. But I love so Tane is a Māori name, which is Tane Mahuta, which is God of the Forest, who I was named after. And it's about, Tane was the son of Papa Earth, Mother Earth, Papa and Maori, and Rengi Sky, so Father Sky. And he was in between them, and he actually pushed them apart to create life. I planted all the trees upside down. Tane planted all the trees upside down, made heaps of problems, squabbling and everything, but eventually made the sun rise again with the fish hook and brought it out of the ocean because they're an island culture. And that beautiful thing of creating mythology and stories that say that the sun comes up for a reason. And Father Sky and Mother Earth are fundamentally connected. They work together. They give birth to life. And that fusion of both out there and down here is so important to so many cultures.
Yeah. That's so beautiful. Thank you for sharing that. That's awesome.
So I want to kind of step back a little bit from, final question. Also, this is something I'm very curious about, just in terms of sort of traditional knowledge. And then I want to fast forward again to the modern day and talk about some more crazy new space facts. But just while we're on this subject of traditional knowledge, one of the things that's most fascinating about your work is that you have discovered that potentially our ancestors, or your indigenous ancestors, may have known about the rotation of the planets and how our solar system worked way before Galileo. Can you talk a little bit more about that, please?
Yeah, it's a huge discovery, or a huge recovery of knowledge, I should say. So while we did know a lot about the stars, we had a very intimate knowledge about the planets as well and how they moved. So one really great thing that I loved learning about was from the Waterman people up in the Northern Territory, is that they had a very, very intimate knowledge of the planets that we fortunately do know about today. And there's this one part that talks about the planets being ancestral figures, walking a path in the sky. Now that path being the ecliptic, which is the apparent path of the sun, and that's where the planets tend to be because of the formation of our solar system. The planets were formed within this accretion disk around the sun. And so we often see our planets very, very close to where the sun is in that apparent path in the sky. But there's a beautiful part to this as well, even more beautiful, I should say. It all is fantastic, is that while the ancestors are walking that path, they're walking forwards, but also walking backwards, which links to this retrograde motion that we observe with the planets because of the structure and the geography of our solar system, us being the third planet from the sun. We see Mercury and Venus kind of swing back and forth around the sun, but we see the other planets, Mars, Jupiter, Saturn, those are the visible ones that we can see with our eyes. We see them going forwards and backwards sometimes, going retrograde and prograde. So seeing that intimately is a huge, huge thing. And actually being able to articulate that in a way within the culture is amazing.
Yeah.
Yeah, I love that.
So much knowledge lost as well. I think just to acknowledge that as well.
Yeah, it's really sad.
Yeah, that we've lost so much, but it's also wonderful that we are regaining some of it. Okay, can we please fast forward to today? I would like to ask you about tidal disruption events.
Oh yes, the
What is
fancy
a tidal
word.
disruption event? Why is it cool? What's just happened? Can you please get your space geek on and tell us about tidal disruption events?
Definitely. So a tidal disruption event goes by another term that many people may have heard of before, and it's called spaghettification. So fantastic, right? Like we have some great terms in astronomy and some great fun terms as well. So this tidal disruption event, we actually observed one. Astronomers observed one happening in real time over the course of about a year of observations in a galaxy X million light years away. It was very far away. But they saw what's a supermassive black hole at the center of this galaxy, completely obliterating and gobbling up a star. So you had this supermassive black hole and a star that's in orbit around the black hole, but at some point it gets just a little bit too close, and the forces involved within this star, being so close to the black hole, the near side of the star to the black hole experiences a much stronger gravitational pull than the far side. And so that pulls it apart, tidally disrupts the entire star and strings it out and stretches it out into a long piece of spaghetti, which then goes into a very, very quick orbit. It's not really an orbit anymore because it's just completely obliterated, but it forms this accretion disk around the black hole, which superheats it. It's going very fast. There's lots of friction going on there. There are jets shooting out from either end of the black hole, kind of like a spinning top. So you got the spinning part here and jets coming out that way. And it's quite a, for lack of a better word, disruptive event.
Very violent.
Well, what does it tell us about the universe? And, why is it so relevant to physics and astrophysics? Like, what does it actually tell us about the space-time continuum? And why does it go all spaghetti? Why is that important?
Well, the reason why it's important and exciting is that we don't see this happen very often. And we have to be looking at the right place at the right time to really see this and get this intimate look at what's going on. So it probably tells us more about how black holes probably consume mass. I would like to say I'm not an expert on black holes. It was a very interesting part of my solid state honors class, but it was very intense, lots of very interesting and quantum mechanically loopy stuff happening with black holes. But being able to intimately see that and have it happen in real time, live almost, is a huge, huge feat. Because another thing that's difficult about seeing this, even within our own galaxy, there's lots of stuff in the way. And these things are at the centers of galaxies. So we have to peer through a lot of stuff just to see this happening, let alone see it from a galaxy that's millions of light years away.
Totally. I mean, Star Wars was right. it's always a long, long time ago in a galaxy far, far away.
Exactly.
Nice.
And also these events tell us that, light can be bent and time can be bent. So it's really cool. I mean, astrophysics makes us fundamentally question everything. And that's what's so cool about it. And it constantly changes its mind, which some people think is uncertainty, but I think that's progress. If everyone's stuck in their ways, then no one is listening. But if you can listen to yourself here on planet Earth and also observe stuff from past time and from things a long, long way away, and things that are so big you can't even comprehend how big they are, that is truly mind-bending and truly mind-expanding.
Exactly. And you've raised a very interesting point and a very important point here as well. And I've seen this a lot, especially with I make a lot of videos on TikTok and put out some fun science little grabs within 60 seconds. And there's this one video that keeps getting comments on it every now and then. It gets put onto the For You page and people see it and like, let's comment and do things and start the conversation. But it's this video about one of the oldest stars in the universe. So it's a star within our own galaxy. It's about 200 light years away. But when we observe this, when we look at a star and we try and work out the age of the star, what it's made of gives us a very good idea of how old it is, generally. So let's say how much oxygen's in it, how much carbon's in it, how much nitrogen's in it, other what we call metals. So just by the way, in astronomy, our periodic table, I have one right here. This is a normal periodic table. An astronomy periodic table is hydrogen, helium, metals. That's it.
Okay.
That's all
You're
it
so
is.
divisionist. Wow.
I know.
So binary.
It's a lot. Although I have to say, learning stellar astrophysics, I actually was having to look at this the other day and be like, what's OS? What is this element? I don't know what this element is. it's a metal.
Yeah.
But yes, so metals tell us, the metal content of a star tells us a lot about how old it is and all that jazz. Now, this particular star, there's a paper about it. It was probably published in early 2000s saying that the age of the star was 14.46 billion years old, plus or minus, I forget what the error is, but
a few billion.
a few billion years old, plus or minus a few billion years, which raises questions because the universe is 13.8 billion years old.
Yeah, wow.
So how can there be a star that's 14 billion years old that's older than the universe? But the thing is when you read this paper as a scientist and who understands the language and all of that, is that the error margins of this age actually do agree within the error margins of the age of the universe. So it's okay. It's not breaking the laws of physics or anything. It's okay. But then people commenting on this is like, oh, uncertainties. So you actually don't know anything. Haha. It's like, no, we do. We do. We know it within this range. But then later studies have a look and bring that age much closer within this accepted age of the universe. So that's the thing, right? Like our understanding and the technology changes and evolves. We're constantly learning new things. Our technology and our instruments are improving. That allows us, and our analysis is improving as well, which allows us to make better estimates. Doesn't mean we know nothing. It just we're learning more and we're improving on our knowledge.
Yeah,
Yeah, absolutely.
All right, so just a quick little pause here. Now, we have people who are watching this live. If you have questions for Kirsten, if you have any space questions you would like answered, please ask them in the question box down here. We're going to spend about 10 minutes asking Kirsten questions from our live audience. If you're tuning in live, you might as well take advantage of it. So please, any space questions that you have, ask them in the question box over here. While everyone's thinking about their questions, I'd also like to tell everyone that you can follow Kirsten on Twitter. There's a button down here as well. That's a good way to keep up with what she's doing, to check out what she's up to. She also has links to her other social media handles. And Kirsten is a star on TikTok. So if anyone's curious about that, it's a pretty good introduction to TikTok and what's possible on that. I also wanted to talk about metals very quickly and how powerful stars can be in forming metals, and in particular in forming gold. Can you talk a little bit? Can you give us some gold facts about stars, please, Kirsten?
I can, and I would love to, because it gives me an opportunity to share with you one of my favorite space facts, but also favorite but kind of useless, but it's hilarious. So in 2017, LIGO, the Gravitational Wave Observatory, observed gravitational waves coming from 2 neutron stars. So a neutron star is a very, very dense remnant core of a massive star. So when you have these dense objects, you have white dwarf stars, which is what our sun will turn into in about 5 billion years or so. But then much more massive stars turn into neutron stars. And just to give you an idea of how dense these things are, a little teaspoon of neutron star matter weighs the equivalent of Mount Everest. So they're really dense objects, like really dense. And so when these 2 neutron stars collided, they produced what's called a kilonova. So it's this huge, dramatic, energetic event which caused a huge amount of energy, which then with that explosion produced a lot of very heavy elements, very heavy metals like silver, gold, and platinum.
Sorry, can I just say, by the way,
Yes.
that kilonova could be potentially the greatest word in the English language.
I know, right? It's so cool. So with this huge explosion, the amount of gold that was created, and we could see how much is created because when we observe it with telescopes and observe the spectra, so the rainbow of this object, we can see how strong these particular gold lines are. So when we look at a star, we look at an object, we see different lines in the spectra that tell us what it's made of. And so we can see how strong this gold is. And we essentially figured out that about 10 Earth masses of gold was created in this intense explosion. Like just our entire planet times 10 gold.
Attention, gold digger alert.
Pretty
Gold
much,
digger
right?
alert. Look for that.
But here's where the fact gets useless, right? So imagine 10 Earth masses of gold, and in today's current gold market, that would cost around, or be valued at around $100 octillion, which is a huge, ridiculously huge number. So just to give you an idea of how big it is, if you want to type into either the chat or something, it's a 1 with 29 zeros after it. So it's a ridiculously massive number. I think I would wonder if there'll be enough characters in the chat box to put it up. But it's a huge, huge, huge number. So see, there you go. That's $100 octillion.
So it's not the 1%. It's the 0.00000 times 29 1% that we got to watch out for.
Exactly. So now with that, it's $100 octillion. Imagine $100 octillion in Australian $2 coins, and I wish I had a $2 coin with me to show non-Australian people who are watching at the moment. But it's just a small coin. It's it's relatively thin. Imagine stacking your $100 octillion of $2 coins on top of each other flat like this. That would create a stack that's long enough to go from the Earth to the point where these 2 neutron stars collided in space and back again about 100 times.
That's pretty good.
That's the most useless fact ever. It's wonderful.
Yeah.
Speaking of gold, I think it has a use that makes it more valuable than money and stacking them to neutron stars, although that is pretty valuable to be, or jewelry or as a precious metal. Like scientific studies of our neurons in our brain have revealed that they contain a trace of gold, and it's critical in the transmission of our electrical signals throughout our body and our mind, and it frankly keeps us existing. So with this tiny amount, minuscule amount of gold in our bodies, we wouldn't be able to turn the most complex biological system, our brain, in the universe, we wouldn't be able to function, we wouldn't be able to use it, we wouldn't even be able to think about stacking $2 Australian coins to 2 colliding neutron stars and back again. That is what's so cool about gold.
That is awesome. So we all have to thank those 2 neutron stars that collided once many, many millions of years ago for the gold in our brains.
Yeah, I can't complain with that.
So that's a lot of stuff around astrophysics, stars, space. Can we talk a little bit about technology? And then we do have a question here from David, which I'll get to next. But can we talk a little bit about technology? I want to talk about 2 things that I really love in space. Telescopes and rovers. We've got two very exciting new pieces of technology that are going to turn on pretty soon within the next few years. One is the James Webb Telescope, and the other thing that's going to be turned on is the new Mars Perseverance rover. Can you talk to us a little bit about those two new technologies and what those two things are going to mean for our understanding of the cosmos?
Definitely. So I would love to start with Percy, little Perseverance rover. Very excited to see that get there very, very soon. So Perseverance was launched a couple of months ago from the Earth and will eventually get to Mars in February 2021. So not much longer to go now, which is a bit of a terrifying thought, to be honest, but very, very exciting as well. So Percy, when it gets to Mars, is going to be landing in the Jezero crater. And this is potentially a place where water, liquid water, could have been on the red planet. Because when we look at this Jezero crater area, it has what looks like very similar to river deltas. So feeding into this crater where they're that's pretty much evidence of previously flowing water. And so when it's there, it has so many really cool cameras and instruments. Oh my goodness. So this particular rover, my favorite instrument is this laser that it has. First of all, everything's cooler with lasers, right? So it has this laser that's literally going to go pew pew to like rock samples to try and figure out what it's made of.
So cool.
With a laser. It's so cool. It also has like 23 cameras. So Percy, I expect lots of selfies.
Yeah, nice. Okay, great.
Yeah, but then when we come to the James Webb Telescope, James Webb is a very interesting telescope. It's going to be fantastic. So it's about 6.5 meters wide. It's going to see into the visible and the infrared spectrum, so the redder than red part, which will hopefully allow us to see maybe planets forming. Or one of the big goals of the James Webb Space Telescope is to peer into the very, very distant universe and try and maybe find what's called a population 3 star. So when we look at our stars, they come in two populations that we can observe. Then we have a theoretical third population. Population 1 are very, very young stars, like our sun. They have lots of metals in them, so they're very, very young. Population 2 are very metal weak and metal poor stars. They're a bit older in the universe. And these population 3 ones are the theoretical first stars that have virtually no metals in them, very, very hydrogen and helium abundant, and very, very massive and hot. They should exist very, very far away in the universe, 13.7 billion light years away. And using that infrared technology with the James Webb Space Telescope and the large mirror, hopefully we might be able to find traces of population 3 stars. However, can James Webb just go up already? It's been delayed and delayed and delayed. I heard a story about how once they shook the telescope and bolts and screws fell out. It's like, oh no, that's not good. So hopefully it will be launched in March 2021. We'll see how that goes. There's a great XKCD plot of like the prediction of when it's going to be launched, and we'll see. Fingers crossed. But it's going to go to a really cool place, and I mean that literally. It's going to go to what's called a Lagrange point beyond the moon. So this is a point that will move with the Earth relative to the Earth, the moon, and the sun in a very stable orbit. So it's going to be very cold out there, far away from the sun, far away from the Earth, far away from the moon. And that's good because we want to keep those instruments for the infrared part of the spectrum very, very cold. Because if it's warm, it's going to mess up with the instruments. So very exciting. Please launch in March 2021. We want to see some really cool science from the James Webb Space Telescope soon.
Yeah, and I think just a side point, imaging in general is one of the unsung heroes of science, whether it's taking a picture of a single atom or taking a picture of the furthest galaxy away. It gives us so much insight into the world and the universe that we live in. So yes, more imaging.
All right, we do have some questions from the audience here. Tane, maybe you can help field them.
All right. So do we have any information about US astronauts saw in space and the structures of the moon that no one is supposed to know about?
We'll leave that one to Kirsten.
No.
Well, okay, I don't work for NASA, so I do not speak for the organization or anything like that. But let me just make something very, very clear. Astronomers and scientists, we're terrible at keeping secrets. Like the news with phosphine leaked a day before the embargo was lifted. Like if we if we find aliens, for example, because that's always a big one. It's like, do you believe in aliens? Have you found aliens? Is something you're not telling us? We will tell you. We're terrible at keeping secrets. So I can't speak about anything that's potentially, I don't know, secret on the moon. We have lunar orbiters that have literally taken photos of the entire moon. So not much to hide up there, to be honest.
Yeah, and I agree. Like, if you're doing proper science, it insists that it's peer-reviewed. So you got to tell someone. So, like, we have to
Exactly. We have to tell it.
It's fundamental. All right, cool. Let's go for a question from David. Was there something somewhere, i.e., where the bits that we call our universe, etc., came from?
I think what David's asking there is where did how did the universe just spring into existence? You can't get nothing, right? Where did this stuff for the universe come from?
Short answer, I don't know. Like, it's a cop-out answer, but like it's as far as our understanding of the universe goes, is that we can't describe anything before the universe. But a common misconception about, let's say, the Big Bang is that it was an explosion in space, but that's actually not quite correct at all. It was an explosion of space. So our universe, the entire universe is infinite. So there is no edge, there's no center, there's nothing like that. Our observable universe is very different. We can see a finite edge of the observable universe. It's about 45 billion light years away. But there is no edge to the entire universe, because our universe, while it did used to be much, much smaller than it is now, it's hard to explain because we're so used to living in a three-dimensional world. And let's say, like, we have a box, right? There's stuff inside the box, there's stuff outside the box. That's kind of the limit of our understanding of the universe. There has to be something outside of it. It has to be expanding into something. But no, it's just space itself used to be much smaller, and space itself expanded and is expanding as well. It's
a question that you could take 2 hours to answer that one, but I think you've done very well in answering it in 1 minute.
Thank you.
Final question here. We've got one from Peter. Who wants to know if you are aware of the theories of plasma cosmology that suggest that essentially several dreaming stories are historical records of solar instability. You can read the question there if you look up the questions, but that's actually a very interesting question. I'd love to hear your thoughts on that.
Let's see which one is it? Okay, plasma cosmology. It's really interesting. So when talking about plasma cosmology, I'm going to assume that we're talking about the sun and like solar mass ejections and stuff like that. So, which is an ejection of material from the sun in our general direction, or in any general direction. But sometimes they can be in our direction. And when that happens is the charged particles that are ejected from the sun in these mass ejections, they interact with the Earth's magnetic fields, and their trajectories are changed because of that interaction with the Earth's magnetic field, which brings them generally towards the poles, whether that be the North or the South Pole, both. And we can see what's then called the auroras. So maybe that's what's linking with the rainbow serpent there. This is just straight off the top of my head. Maybe that's a connection. I'd have to learn more about the particular stories and talk to elders and all that jazz. But I don't doubt that Aboriginal astronomers would have observed that and made connections in that similar way.
Yeah, and most of our planets in our solar system have auras as well, which most people don't know. I have a question for you. one of the biggest criticisms of space travel and astrophysics and astronomy, why are you looking up instead of looking down? We've got problems here, but so why are we spending so much time doing that? Any thoughts? It's a tough question.
It is a tough question because I totally agree. There are problems here on Earth that we do need to tackle as well. But look, the thing is, you can chew gum and walk at the same time, right? You can do more than one thing. And it's so important to keep fueling curiosity as well as, dealing with real world problems and all of that jazz. But also looking up at the stars and understanding more about our universe and how it functions can help us here on the Earth as well. As a more of a roundabout example is with the Apollo missions going to the moon. The Apollo missions gave us Velcro. And they gave us, what's it called? Those special pillows, memory foam, that's it.
Yep.
The Apollo missions gave us memory foam. That's what the astronauts sat on, memory foam. So if you have a memory foam mattress or a memory foam pillow, that's because of the Apollo missions. Okay, it's a bit of a, not quite a, real world problem, so to speak, but, or a big problem, so to speak, but it's our understanding of space and universe can help us a lot. Wi-Fi as well, for example, developed in Australia. There are ways that this can help us without directly helping us, without directly having to solve a problem.
I mean, one of my favorite is from the Apollo missions is the picture of Earth called Earthrise.
Oh, I love that photo.
Early 70s. And it showed us a world without borders. Looking at our planet as a whole, and you see massive environmental movements starting. The EPA was formed. It gave us water filtration, air filtration, solar energy, it gave us diapers. So when we're on Zoom meetings too long, we don't even have to move. And it's incredible, and it gives us a certain perspective that we've never had before until recently in the last few decades. And it teaches us about the small and the large, and it's guided ancient civilizations, and it still guides us today. It is paramount, and hashtag choose both and all that jazz.
Exactly.
So Kirsten, we have run slightly over time here, so we're going to wrap it up. Just any final thoughts? And what we will usually like to do here is, do you have any questions or a question that you would like the audience tuning in today to ask themselves over, let's say, the next few weeks or months? What is one question that people who are watching this video can ask themselves over the next little period, something for them to think about?
I think the question I'd like to pose to the audience is, how can you help recover Indigenous knowledge? Whether it's from Australia or from America or from anywhere around the world, there are Indigenous peoples from all around the world. How can you help give a voice to those Indigenous peoples to help recover knowledge where it has been lost and appreciate more about our ancient cultures and our still living Indigenous cultures as well? Because it's important to see where we've come from to go forward.
Fantastic. We could not agree more. Kirsten Banks, astrophysicist, proud Wiradjuri woman, amazing science communicator, and totally dorky space geek. It's been a wonderful conversation. Thank you for joining us on Future Brunch. Everyone, could you please show your appreciation? Any comments, observations, or just a word of thanks, please put it into the chat box. This is Future Brunch. We've really enjoyed this. Tane, any final words?
Just the ability to nerd out on space is so cool. I even wore my favorite socks, which are beluga whales, with an astronaut riding them through the stars. I think it's so important to look up occasionally because we have the blinders on. And I love Future Crunch, and I love the people that we get to chat to. It's basically an excuse to nerd out and to find stories of human progress, old and new. And that's what it's all about. So I'm excited.
Yep, thanks very much. All right, that's it for this Future Brunch. We will see you in 2 weeks' time. Kirsten, thank you again.
Thanks for having me.
Thank you,
Thanks, everyone.
Uh,